Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about graphing and writing equations of ellipses. All right, so we're going to talk about characteristics of ellipses, graphing ellipses, and then writing equations, so using the process of completing the square to rewrite equations in general conic form. All right, so characteristics of ellipses. So we're going to create first we're going to talk about the definition of an ellipse, then we'll create an analogy that's relevant to my homestead brethren. All right, so an ellipse is a set of all points such that the sum of the distances from the foci and any point on the ellipse is constant. So we talked about the circles first, or circles, and we said the circle was a set of all points that are equidistant from a fixed point called the center. And so now we're moving beyond. Now we really have two centers, and the centers are moving apart from each other. And what happens is that that distance now becomes, instead of one distance from the center to the point on the circle, now we have two distances, but the sum of the distances, d3 plus d4, is equal to d1 plus d2. So the sum now of the distances from the foci and not the center, which would be in the case of the circle, is going to be constant all the way around the ellipse. So that's how we get the elongated, kind of the egg-shaped feature of the ellipse, because now we're using, instead of one center, we're using two centers. We call those centers foci, not to be confused with the actual center for the ellipse. But relative to the circle, we've now separated the centers out into two foci, and now the sum of those distances is going to be the same all the way around the ellipse. All right, so let's take a look, just for fun, at what this might look like in terms of a football field, which is in the general shape of an ellipse. We have the foci, which are the football. We have the vertices, which are the goalposts. We have the center, which is the happy face. And then we have the co-vertices, which are the cheerleaders. All right, so the distance from the foci to any part of the edge of the track is going to be constant. So d1 plus d2 is going to be constant all the way around the track. All right, so the two footballs again are the foci. The line between the goalposts we're going to call the major axis. And then the line between the cheerleaders we're going to call the minor axis. So the major axis is the elongated, goes right through the center of the elongated portion of the ellipse. Minor axis goes through the narrower portion of the ellipse. Okay, so it's possible to have a major axis that's vertical and not horizontal. And we'll go through the different equations for both vertical and horizontal major axis. But the ellipse orientation, as far as we're concerned for now, does not have to be, major axis does not have to be horizontal. It can be either horizontal or it can be vertical. All right, so now we're going to go to a layout of the ellipse with a horizontal major axis. I'm going to give you some letters, and I'm going to ask you to connect them either to the football, which we said was the foci, line connecting the goalpost, which is the major axis, line connecting the cheerleaders, minor axis, happy face, which is the center, goalpost is the vertices, cheerleaders as the co-vertices. And I want you to identify and write down the value associated with each of the letters here. I'm going to pause and then move on. All right, so you can see that A is going to be a co-vertex. It's the cheerleader, plus 6. B is going to be the center, happy face, plus 4. C is going to be the major axis, line connecting the goalpost, plus 2. And then G is going to have no meaning. So remember, the foci have to lie on the major axis. D would be the foci. All right, next set. So provide the sums of D, E, and F, and now we're converting them to their actual names. Not the name for the analogy of the football field. All right, so D would be a focus. E is going to be, so that's plus 1. E is going to be a vertex, so plus 5. And the last one, F, is going to be the minor axis, so that's going to be plus 3. All right, so same thing with a major axis. It's vertical, A, B, C, and G. And pause here. All right, so A is going to be a co-vertex, B is going to be the center, C is going to be the major axis. Now, Then G, again, will have no meaning. So again, the focus, or the foci have to lie on the major axis. There are no points that are relevant on the minor axis except for the co-vertices. Same thing for D, E, and F. So we see D is going to be the minor axis. That should be +2. E is going to be the E is going to be the vertex, so +5. So D should be the minor axis. It should be +2. And then F is going to be the focus. So focus is +1. All right, so ellipse A, B's, and C's. All right, so I'm going to give you the formula for a horizontal ellipse with a horizontal major axis, x minus h squared over a squared plus y minus k squared over b squared is equal to 1, where hk is the location for the center of the ellipse. Hk should be familiar to you from our discussion about circles, and also when we talk about translated functions. This is not the first time we've talked about hk. So the center is hk. And now let's talk about A. A is going to be the distance from the center in both directions along the major axis to the vertices. So A is going to be this distance here from HK along the major axis to each of the vertices, both left and right. So we're going to add or subtract values from the x part of the coordinate for the center. The B value is going to be the distance along the minor axis from the center in both directions. So again, B units up and P units down where the major axis is horizontal. And then the C value is going to be the distance from the center in both directions along the major axis to the foci. And there's a relationship between these distances. So C squared, C is the value or the distance from the center along the major axis to the focus. A is the distance from the center along the major axis to the vertex, and B is the distance from the center along the minor axis to the co-vertex. C squared is equal to A squared minus B squared. Now there is a relationship to the Pythagorean theorem, but the letters are, in a right triangle, but the letters are going to be different if you set up the triangle for the distances. So A, B, and C relative to a right triangle A and B, which are the legs, and C, the hypotenuse, will be different. So there is a relationship, but not set up according to the letters in what you normally see in a Pythagorean theorem. Okay, so again, C is the distance from the center to the focus. All right, so now I'm going to give you the vertical major axis, y minus k squared plus x minus h squared over a squared and b squared respectively. So you see now the difference really between the two. The only difference is that now with a vertical major axis, a squared is going to be underneath the y squared term, right? Whereas with the horizontal major axis, a squared was underneath the x squared term. Everything else is the same. H and k are still with y and x. These are both positive terms, so it doesn't matter what order they go into. All right, so the secret to figuring out vertical versus horizontal major axis is to take a look at the denominator, and the denominator that has the largest value will be the denominator with the a value. When the a value is largest underneath, or the value of the denominator is largest underneath y, then you're going to have a vertical major axis. Okay, so again, vertical orientation, horizontal orientation. The only thing that you should notice is the difference, the location of a squared and b squared. And the way to tell which value is a squared is the a squared value is always going to be the larger value. And you can use that to identify what the orientation of the ellipse is. So I'll just preface it's going to be a little bit different with hyperbolas, so just keep that in the back of your mind. This is only for ellipses. All right, so k stays with x and y. A squared is always bigger than b squared. A squared is the denominator under y for vertical major axis and under x for the horizontal major axis. Okay, so we talked about these before, so this is just a summary. All right, so now I want you to answer the following questions. I'm going to stop and then move on. All right, so we see that the larger value is underneath the x squared numerator, so we know the orientation is a horizontal major axis. A is 7, B is 3. We figure out C as 2 root 10. Same thing. And yes, this is sort of a trick question. The only thing that I've done from the prior equation is I've just switched the terms in order, but the equation for the ellipse is still the same. So it's still horizontal major axis, A is still 7, B is still 3. So the term with the a squared value doesn't have to be the first term in this case. So just look for the denominator with the largest value, that's the a squared term. Okay, graphing ellipses. So this is the process of graphing ellipses. I'm going to let you write this down as I pause. All right, we're going to take this particular ellipse and we're going to graph it. So we're going to identify the orientation. Orientation is going to be horizontal. A squared term is underneath the x squared value. Identify the center, negative 1, 3. Find the a value. A value is 4. 16 squared is 16. So a squared is equal to 16. A is equal to 4. We're going to identify the coordinates for the vertices. We're going to move 4 units along the major axis in both directions, so negative 5, 3, and 3, 3. Now we're going to graph it. We're going to find the b value. B value is going to be the square root of 9. And then we're going to find the c value using c squared is equal to a squared minus b squared. We're going to move 7 units along the major axis in both directions. So b value is 3. We identify the coordinates for the co-vertices moving up and down respectively from the center. We identify the c value as the square root of 7. And then we move left and right along the major axis. Minus 1 plus or minus the square root of 7, comma 3 will be the coordinates for the foci. And you can just leave it for my classes in this form when I ask you for the coordinates for the foci. Okay, so now we're graphing still. Foci here graphed. All right, so now I want you to do the same thing for this equation. I'm going to move through this very quickly as I pause here. Oh, actually, you're going to have to do this on your own. I don't have the answer worked out. Okay, so supplementary graphing, if you want to work on this equation, you can. Okay, let's see what I have next for you. These are all supplementary graphing. Okay, so now writing equations for ellipse. So now we're going to take a graph and we're going to write an equation for ellipse based on the graph. All right, so here is the graph. So first step is to determine whether or not it's vertically oriented or horizontally oriented ellipse, and then find the HK values. You see it's a vertically oriented ellipse. We'll find the distance from the center to the vertex is going to be the longest length here. So it'll be vertical, and then we determine the coordinates for the center, 7, negative 2. So I can write my equation, y plus 2 squared over a squared plus x minus 7 squared over b squared is equal to 1. Now we have to find the values for a and for b. So we find the distance from the center to the vertex, center to the co-vertices, 7 and 3 respectively. So now it's y plus 2 squared over 49 plus x minus 7 squared over 9 is equal to 1. All right. So write an equation for ellipse with its center at 3, negative 2, a vertex at 3, 3, and a focus at 3, negative 6. I'm going to let you take a moment while you do this. We're going to have to wrap up shortly. This is the answer you should get. All right, so now we're going to move on and we're going to talk about writing equations from general conic form and converting those to standard form. So here is my equation in general conic form. I'm going to convert to standard form. So we're going to group the terms with x and y, move the constant to the right-hand side of the equation. Then we're going to distribute the common constant factors from the group terms. And then we're going to complete the square. So remember, when we add in this value for 1 here, we have to add 49 times that value. So we're going to have 49 to the left or to the right-hand side. We're going to rewrite the equation that we had from the previous page. We're going to rewrite as a squared binomial. 49 times x minus 1 squared plus 16y squared is equal to 784. Now we want this to be equal to 1. So we're going to divide both sides by 784. And then we're going to simplify the terms. And we end up with x minus 1 squared over 16 plus y squared over 49 is equal to 1. All right, that's it for this edition of Ott in Math. I hope you learned a lot. Join us next time when we talk about hyperbolas.